Hello, welcome to this episode solving the LeetCode problem 162, find peak element. And here peak element is an element that is strictly greater than its neighbors. And it means if there is a number in an array, the number before it and the number after it cannot be the same. Uh, so two numbers which are adjacent to each other has to be different. And this array is zero index. And then once we find the peak element, we have to return its index. So when you're returning, we have to return between 0 and up till the length of this array. The search space is basically starting from the beginning and the end of the array. So in this example, 0, 1, 2, 3, 4, 5, 6, there are 6 values. So the peak is probably at 6 because uh, if you start from 1, then it goes to 2, then 1, then 3, then 5, then 6, then 4. So there is one peak at 6 and another peak at 2. So 2 is at index 1 and 6 is at index 5. So you can potentially return either of them and it's a valid answer. Uh, so this is how the problem is formulated. And this piece says you may imagine that numbers minus 1 equals numbers n equals minus infinity, which means if you had only one number 1, how would you define is it a peak or not? So it's basically saying that any number minus 1 indexed, which is basically before this, it is supposed to be a negative infinity, and numbers of n. So it is zeroed index, this is negative 1 index, and there is only one value. So the length n is equals 1. So the one index value should be here, so it's going to be negative 1, negative infinity as well. So in other words, if there's one single value, you can assume that this is the peak itself. So this is what it is trying to explain. In other words, an element is always considered to be strictly greater than a neighbor that is outside the array. So this is what I just explained visually. And it says you must write an algorithm that runs in order of log n time. So if you had an array like this, you could do a linear search by looping over each of these values and see a value like 6 or 2 is less is strictly greater than the number before and after it. And if it's valid, in that case, you have to just return the index. And that would give you a time complexity of order of n because this is linear. You have to just look at every single number in the array, and the space complexity would be order of 1 because we're not keeping extra space. But if you are uh, considering the logarithmic runtime, you have to use uh, binary search, and you'll be able to use binary search if you notice there's a pattern in this problem that a value can actually grow like this. If you notice, a value can carry multiple peak. And in a binary search, the values should actually have a continuously increasing or decreasing pattern. They should be sorted with a certain range. And if you have an example like this is 0 and this is the end index value here. So your objective is to find the index for this peak or this peak. And in a binary search, you typically just take the somewhat middle point of the search space and look at the current value. And if you're using binary search, you can probably climb up to the right, up to this side, to this peak, or if your pivot point is right here, and you can probably go to the left to the peak and return this index. The same can be done here. So at any time, whenever you just are searching uh, uh, at a particular pivot point, just compare it with the values around it and decide to uh, slice your search space by half almost. And that's how you achieve this uh, logarithmic time complexity. So that would be log of n time complexity. And that is a way more efficient than linear complexity. Now let's go to implementing this solution. And if you notice, these two numbers are not going to be the same when they're adjacent to each other. And the first thing we need to remember, the search space is going to be between 0 uh, and n. So this is going to be our left and the right edge of the search space. And the midpoint that we have to find is very critical. And midpoint is going to be the middle point of between L and R. So for this example, 1, 2, 1, 3, 5, 6, 4, you basically have to find the indexes 0, 1, 2, 3, 4, 5, 6. This is the indexes. Uh, and when we are following the binary search, you start with left and the right. So this is the left and your right, and if you just find the middle point, and once you find the middle point, you just uh, uh, there are 6 values, so 0 to 6, and the middle point will be 3. Uh, so this is going to be the value we're looking at. We'll be looking at, and now 3 is the value, and you have to just look at the uh, look at its neighbors. And if you have the condition for your binary search until these values meet, left and the right values that are different, which also means there has to be at least 2 values uh, in you when you apply your search. When they are L equals R, it's going to stop. And that is the answer you're looking for. So in this case, at least 2 values should be available. And if your midpoint is going to always return the lesser of these 2 values when the uh, when the search space is reduced to the smallest slice. In that case, you only have 2 values, and this is going to be, if you had only 2 values, this would be the midpoint on the left. Uh, and initially, if you have a three midpoint, you will look at its its neighbor, which is 5, and see, okay, this is actually greater than not greater than 5. So in that case, you can disregard this portion, and you can move your left to at this point. So let me switch the color. Uh, this is your left value now, and you already had right, and you had 3. You can also disregard left and 3, and so 5 up to 4. This is the search range you are now going to uh, run binary search again. And between these 2 values, you will just midpoint is 6, and at this point you will compare it with the value next to it, and you can probably also get rid of 6, and you will set R here between 5 and 6, and at this point, you have 2 values, L and R, and once the midpoint is selected at 5, you will compare it with 6, and you can also get rid of 5. So at this point, your L and R would be both at this point. Index 5, which is basically the value of 6. And this is going to terminate the while loop, and you will get the answer 5, which is corresponding to the value 6, which is the pick. So let's now implement that as we just discussed. So we have to have the search space defined. So this is the first index, L, and the last index would be the last in R. The right side would be the last index of the search region, and we are going to run this uh, binary search until this value is the same. And midpoint would be the middle point between left and right. So the middle point can be calculated by taking the average, but this is a problem because it can run into memory overflow because if L and R both are very large integers or large numbers, they're added when you just add them up, they might be out of range for uh, integer data type and doesn't give you a garbage value. So a better approach is to have L and then take the difference between them and take half of the difference. This is still going to be problematic if you have a very large difference between R and L. So what I personally prefer is to just have a more efficient solution. It can actually just shift the bits to the right, and a bitwise operation is going to ensure that it's exactly the half. And this is a floor division. So if you had a few numbers, let's say uh, uh, 10, 11, 12. In that case, it would actually go to the middle point. But he had only 10 and 11. This is the equation, right? 11 minus 10, and this is basically half. So half of 1 is going to be still 0 because it's an integer division. This is 10. So once we have the thinnest slice of the search range. This is a case you have to consider when you're implementing binary search. In this case, this is the smallest slice, and I just discussed it will only be valid when L and R are the same. If L and R are not the same, when L are the same, it's gonna stop the while loop. So with that, there's a guarantee that there's at least two values, and we know there will be one value in the midpoint, and there will be another value on the right of the midpoint. So if there's a midpoint value is currently greater than the number next to it, in that case, you don't have to worry about the right portion anymore. So in other words, you had this range and 1, 2, 1, 3, 5, 6, and you had this value, and this is currently less than the is next. You are going to just take the left and set it right here at 5. And there's a last value is 4. So R is still at 4, but you're taking your left pointer at the value next to the current value. And otherwise, if you notice these two numbers, mid and mid plus 1, will not be the same. So that means uh, the current mid value is actually less. In that case, if it is less, so in this example, if you had this mid value at 5 and this is less than 6, you can get rid of this, right? So uh, in this case, you're just reducing the search region because you're um, in this case, the alternative case is your mid value is less than the right value. So you are, let me think deeper. So currently uh, in this first example, currently the mid is higher than the, the, the next to it, right? In that case, if it is 3, 5, 6, 4, and if you and 1 to 1, this is your left and this is your right and this is your mid, and mid is actually uh, greater. In that case, you would, if this is a if it was 7, in that case you would actually just won't have to worry about this. You just put R here. So let's take our example that we currently have. So we have 3. This is a 3 value, 3, 5. So 3 is less than 5 in that case. We're just taking L and putting it at right here. Okay. So now that makes sense. So if this is current value is less than next, so you just set uh, L to be to the right. So you're just disregarding the left side. Otherwise, you are just going to know that current value is greater. So in that case, you have to just disregard the right side, and this is going to be your reduced search space. And at this point, when this condition terminates, this is just going to be AL equals R, and that is a value you're going to look for. So we can run this now and see if it passes. Yep, and you can also submit that. Yep, it passed with a runtime complexity of It has a runtime complexity of order of n, logarithm order of logN, and the space complexity is going to be order of